need a comfort.
I want to securely store
I need
value.
to keep time.
I want to
hydrate. I need a place to rest and read outdoors.
We humans have many demands in our daily life. In this video, we will introduce our proposed benchmark, multi-object demand-driven navigation. We also propose a coarse-to-fine attribute-based exploration agent named C2F agent to solve this benchmark. In this benchmark, a user gives a natural language instruction, and an agent needs to understand the instruction and find the corresponding objects in the scene. The user's instructions may be complex and require finding objects in different locations, which in the end will make up a solution. Now we will demonstrate how the agent completes a MO-DDN task by finding objects that meet people's demands. Initially, the agent will be randomly placed at a location. Then the agent receives demand instructions, including basic and preferred demands. In the example in this video, the user wants to organize separate activities for his friends and their children. The agent is randomly initialized in the garden. When the agent walks around the gardens, it firstly finds toy slides for the kids to play on. Then the agent finds beanbag chairs and umbrellas for the adults to rest on. The agent walks indoors, finds armchairs and some kitchen items that can be used to prepare lunch. Specifically, the agent finds a saucepan for stews and an oven for baking food. Then the agent finds a refrigerator with food but no ice cream. To prepare for dinner, the agent found plate, knife, and fork. The objects needed for lunch have already been found. The agent walks out of the kitchen area and into the living room area, looking for rest and entertainment, like sofa and TV. Ultimately, the agent visits several areas and meets the user's basic demands and some of his preferred demands, but does not find the ice cream. For this task, we will introduce our coarse-to-fine attribute-based exploration agent. To train the attribute model, we propose 3 kinds of losses. Attribute loss is for instruction MLP encoder to fit ground truth attribute features. Matching loss directly aligns the instruction attribute feature with the object attribute feature. VQ loss, commitment loss, and reconstruction loss indirectly guide the instruction and object attribute feature into the shared codebook, aligning these 2 attributes. The function of the attribute model is to map a demand instruction or an object category to several attribute features that are in the shared attribute feature space. We first build point clouds of the scene with a depth camera, and then label the objects in the field of view with an object detection model and map them to the point clouds. The point clouds are then segmented into blocks according to X and Y coordinates. Thus, each detected object will belong to a block according to the center of the object's point clouds. Then, we compute the cosine similarity between object attribute features and instruction attribute features in each block as the score of the block. Finally, we randomly choose a point in the highest scoring and never visited block as the waypoint, and then a path planning algorithm is used to navigate the agent to the block. Next are more block visualizations of the coarse exploration phase. A darker red color means a higher cosine similarity between the attribute features of the objects and the instruction. The darkness of the color is based on the rank of the block score among all blocks, not the actual score. Since scores are not calculated for blocks that have been visited before, only a single coarse exploration is included in the visualization. Note that the block with the highest score is likely to contain objects that can satisfy the demands. We train an end-to-end module for exploring within blocks. The self-attention mechanism in the transformer encoder learns the association between the attribute features of the objects in the current field of view and the attribute features of the instructions, which improves the efficiency of the search within the block. Our method outperforms the baseline in the vast majority of settings. Attribute similarity scores are a good substitute for LLM for waypoint selection. Compared to MOPA plus LLM, which requires 5.15 requests to the LLM per episode on average, ours LM branch only needs to request the LLM to parse instructions into attributes once at the beginning and achieves better performance. The ablation study demonstrates the effectiveness of each part of our coarse-to-fine exploration. Attribute features improve the exploration efficiency at different phases. Thank you for your watching.